Okay, welcome to the session, everyone. So today we're going to be talking about epidemiology, and this is the 10th lecture of MD 6028. So again, epidemiology today, which essentially means we're going to be thinking about viral disease from a more overarching perspective. So a lot of what we've talked about so far has been related to individual health. We've looked a lot at how viruses replicate, infect, cause disease within individual hosts. What we want to do now is take a step back and think about these facts from a population level perspective, because it's really important we do that. There's a lot of information that is really necessary for us to understand viral disease that we can't get from individual cases. We need to get from the population as a whole. We need to get from statistics and big data and things like that. And what we're going to talk about today are concepts related to that. There's also interventions we can use that we implement at a population level rather than at an individual level, and that's also something we're going to think about today. So firstly, we'll be defining epidemiology. We'll be discussing some of the key concepts within epidemiology. Then we're going to talk about some approaches we can take at a population level. So we're going to be looking at population level interventions and think about how these can potentially stop or slow the spread of viral disease within a population. Okay, so one key concept that we need to define at the start is this idea of the R number. Now, again, I think this is something you've probably heard about with regards to COVID, but the R number is an established concept that's been used for a long time by epidemiologists to help us understand how an infectious disease is spreading throughout a population. The R number itself is the reproductive number, and it essentially represents the additional number of infections we can expect from each infectious case. Another way to say this is if we consider a person who's become infected with a particular infectious disease, how many additional infections can we expect to occur as a consequence of that initial infection? It's not a whole number, and this is something to consider, or it's not necessarily a whole number, which can seem a little bit counterintuitive at first, because it can be something like 3.2 or 1.5, and how can an individual infected with an infectious disease infect 1.5 additional people? It doesn't make sense, and that's because the reproductive number is an average, so it's not an actual expectation, it's an average expectation. And because some individuals could become infected and cause a large number of additional infections, while some individuals who become infected could live fairly isolated lives and not pass the infection on to anyone else. Therefore, the reproductive number is an average of all these people. Really important we understand it when we want to understand a particular infectious disease, because when we have the R number, we have a key piece of information about how rapidly we can expect the infection to spread throughout the population. And straight away here is an example, this R number, of information that is useful to us and that we can obtain from individual medicine and individual studies of infectious disease. To get this R number, we need population level data. We need to look at the statistics of how the infectious disease is moving throughout a population. We need to look at the cases, the number of cases. And again, really useful information to us, and the only way we can get it is by analysing an infectious disease at a population level rather than at an individual level. It's important to note that the R number isn't static. When we're talking about COVID in the news and things like that, we'll talk about what the R number is at the moment, and we talk about lowering the R number. This obviously implies again that the R number isn't static for an infectious disease, and the R number is impacted by various factors. These factors can be vaccination levels, these factors can be individual behaviour, whether there are quarantines and things like that. And obviously in the case of COVID, we've spent quite a lot of time trying to bring down the R number. So it's not a static thing. A particular infectious disease doesn't just have a particular R number and that's the end of it. there are factors that impact the R number of an infectious disease, and this is important from an epidemiological perspective because that means there are things we can do to bring the R number down and reduce the spread of infection within a population. And that's a lot of what we'll focus on today. We'll focus on the interventions that we can use at a population level to bring down this R number, and crucially to bring down the R number past 1, because 1 is the critical point. If the R number is rising above 1, then for each infectious case we can expect more than 1 additional infections, which means the overall number of infections in the population is trending up. If, on the other hand, we can bring the R number below 1, that means for each infectious case the number of additional infections is less than 1, and therefore the total number of infections in the population is trending downwards. So 1 is the critical point for this R number. So hopefully that makes it clear that what we're trying to do is lower the R number in our attempt to control the spread of an infectious disease. So again, lower the average number of additional infections from each infectious case. There's 2 well-known approaches, or there's 2 well-known ways in which we can try to do this. It's something we've talked about before. It's something you'll probably be familiar with anyway. It's the idea of the compatibility filter and the encounter filter. And these are, again, 2 broad strategies we can use, or classifications of strategies that we can use to control the spread of an infectious disease. And again, what that means is lowering the R number. The first is referred to as the compatibility filter. So the compatibility filter refers to the fact that there's a barrier that viruses have to overcome, which is the fact that they can only infect individuals that are compatible with that particular virus. So therefore, if we can make individuals incompatible with a particular virus, then the virus cannot infect them, and therefore we should see the R number drop. The encounter filter, on the other hand, refers to this idea that viruses can only infect individuals they come into contact with. The only way you can contract a virus is if you get exposed to the virus, right? So if we can reduce the number of exposures, so reduce the encounters, we can again lower the R number and prevent the spread of infectious disease. These are concepts across microbiology, so it applies to bacterial disease and fungal disease, but what we're talking about here, of course, is viral disease. So we're going to look at some specific viral examples later on. So firstly, the compatibility filter. So again, whether it's a virus or a bacteria or a fungi, it can only, or an infectious agent can only establish infection in an individual if that individual is compatible. So now we want to consider how we can actually put this into practice. So first, like we just said, we're going to think about the compatibility filter and how we can close this filter, so how we can prevent the spread of infection by making individuals incompatible with a particular virus. And then we're going to consider the encounter filter, so how we can reduce the spread of infections by reducing the number of encounters between the particular infectious agent and individuals. So these are the ways we can exert control over the compatibility filter. And again, these are ways that we can make individuals incompatible with the virus, and the same applies for bacteria or fungi. Again, the principles are the same, but here we're thinking about viruses. Previous infection. So this is one way that individuals can gain an incompatibility with a particular virus. So often if an individual has been infected with a particular virus, they will have some degree of protection. It may not be 100%, and it may not last for, well, the time it lasts for will depend on various things, but it's not going to be 100% protection forever necessarily. It's not really what we expect, but there is often some level of protection that lasts for some amount of time. Prophylactic drugs. So for some viral infections, individuals can be given drugs prophylactically. Again, this is a concept we've talked about, the idea that you can give someone, in the case of viruses, antivirals, and these antivirals will inhibit the replication cycle of a particular virus if individuals do come into contact with that virus. So that means while someone is taking the prophylactic drugs, they are incompatible with that particular virus. So you are inducing incompatibility this way, which again is closing this compatibility filter. Natural resistance. So some individuals will just have a natural incompatibility with a particular virus. We've talked at some point about the mutations that some individuals have, particularly in Northern Europe, that confer some degree of resistance to HIV infection. So it's the CCR5 Delta 32 mutation. So CCR5, as we know, is the co-receptor that HIV attaches to. When we're talking about the genetics and things like that, when we say delta, it means missing, so something's missing. So CCR5 Delta 32 mutation means there's 32 residues just missing at the end of CCR5. And this is why these individuals have some degree of resistance to HIV infection. It's not particularly useful from a therapeutic perspective because this is a natural resistance built into some individuals' genetics, so it's difficult to harness that therapeutically. As I'm sure you know, however, it has been harnessed therapeutically in a small number of cases. So there's those 2 cases of individuals who have been cured of HIV because they've had a bone marrow transplant from individuals with this natural mutation. But obviously this is a very extreme intervention, and the purpose of the intervention wasn't to cure HIV, it was for separate conditions because they needed this transplant due to cancer. But the curing of HIV was just a consequence of that. Obviously, HIV in and of itself isn't seen as a serious enough pathology to justify such an extreme intervention as a hematopoietic stem cell transplant. Finally, vaccination, and obviously this is the big one. So we can induce the population to become incompatible or protected by encouraging individuals to become vaccinated. What vaccination does is again induce a level of immunological protection. So an individual who's vaccinated against a particular infectious disease will have some degree of protection against future infection with that particular infectious disease. And again, we don't necessarily expect that protection to be 100%, but we do expect that protection to be significant if it is a vaccine that is being widely used. And again, this is what we do see. Vaccines that we do use do tend to confer a significant degree of protection and play a massive role in making individuals within a population incompatible. And this is essentially what herd immunity is, which is a concept we've again talked about. The idea that if enough individuals in a population are protected, potentially by vaccination or sometimes by previous infection, then the particular infectious agent just will not spread through the population. It will not reach the individuals who are compatible, because those individuals who are compatible are just surrounded by incompatible individuals. Okay. So prophylaxis. So we want to talk about prophylaxis a little bit more here, because there are some issues with prophylaxis. Again, it can be a really useful intervention, but it's not perfect. So first we have to think about who to target with these prophylactic interventions. So it's not reasonable or justified to give a whole population a post-exposure prophylactic necessarily, particularly if there are small portions of the population that are inordinately likely to be infected with a particular infectious disease. And this is what we often see with prophylaxis, pre-exposure prophylaxis. Individuals who are at high risk are given the opportunity to take these therapies because, again, they're at high risk, so it's cost effective to target these people. And in terms of targeting them with advertising and making sure they have the opportunity to engage in these programs, because again, pre-exposure prophylactic drugs are not necessarily cheap. They cost money, someone has to pay for them, so it makes sense that individuals who are at higher risk are the ones who are first given the opportunity to take these drugs. It's important to note that someone being high risk for a particular viral disease can be based upon their circumstance and can be based upon various other factors, and people can be considered high risk at a particular time but not high risk at another time. And a clear example of this is after cell transplantations. So hematopoietic cell transplantations here is the example given, and acyclovir, an antiviral drug that we've talked about, can be used prophylactically to inhibit induce incompatibility with varicella zoster virus, which will inhibit the replication of the virus if it does enter into individuals. And there's good evidence that giving individuals who have an increased susceptibility to VZV infection because they have reduced immunological function because they've had a HCT. There's good evidence that giving these individuals acyclovir, again an antiviral drug, will induce some level of resistance. So again, this is some level of incompatibility, and the end point of this is we see reduced numbers of VZV infections in these individuals. Acyclovir is a drug we've talked about that is very effective at inhibiting herpes virus replication, which of course that's what varicella zoster virus is. So when we're thinking prophylactically, we need to think about the wide range of situations in which prophylaxis can be used. Yes, we have the clear example that has been talked about in the past of antiretrovirals being given prophylactically to prevent the spread of HIV in high-risk individuals, but there's plenty of other examples as well, and here's a really good one. So acyclovir being given in recipients of HCTs to prevent the transmission of varicella zoster virus. It's important to note as well that when we're talking about varicella zoster virus infections in this context, we're talking about an infection that can potentially be extremely serious and fatal, because again, we're talking about an immunocompromised state. So not only can the likelihood of contracting this infection be increased, but the consequences of infection can be far more severe. And we can support this with our knowledge of antivirals. So we know antivirals are inhibiting the viral replication cycle. That's exactly what acyclovir is doing. So acyclovir is inhibiting the genomic processes of these herpes viruses. It's a nucleoside analog, so it's processed into its active form. And in this active form, it causes chain termination. So it prevents the genomic processes of herpes viruses because it's an analog of these nucleosides, not a true nucleoside. It needs to be processed first into its active form, and it is processed by thymidine kinase, which is a viral enzyme. This means acyclovir only converts into its active form in cells that have this enzyme, so in cells that are actively infected with herpes viruses. So in healthy cells, acyclovir does not function as an analog, so it does not inhibit any genomic processes. So a really good example of an antiviral that inhibits the viral replication cycle, and that does so in a specific way to avoid impacting normal healthy cells, so to get around this idea of toxicity. Okay, and here's another example that again we've talked about before. It's the idea that individuals who are at high risk of HIV can be given antiretrovirals prophylactically because these drugs will make them resistant to the acquisition of infection. Obviously not 100% resistance, but they'll give them some level of resistance. What high risk means and what we can define as high risk is contentious, and there's a lot of literature around that. One point that's made here is this idea of serodiscordant relationships. So serodiscordant means individuals who have different serostatus. So someone who is HIV positive in a relationship with someone who is HIV negative. This is serodiscordance, and in these cases it should be pretty clear how the use of pre-exposure prophylaxis could potentially be beneficial. Okay, and here we have another paper that we can look at, and this paper explores this really important idea that once individuals are on a pre-exposure prophylactic regimen, they understand that they have some level of protection against a particular infectious agent, and then what can potentially happen is these individuals can adjust their behavior. So as a result of their perceived increased resistance to a particular infectious agent, they can actually potentially increase their engagement in high-risk behaviors, and this is obviously problematic. One, because no pre-exposure prophylactic regimen gives 100% protection, so these individuals are still at risk of transmission of infectious disease, and also because there are other infectious diseases that can transmit by the same route that the individuals do not have any protection against through the pre-exposure prophylaxis regimen. So here we're talking about MSM, so this is men who have sex with men, and this paper is showing how individuals who are receiving pre-exposure prophylaxis, if we look at these individuals, we see a statistical increase in a range of other STIs, and this is also showing an increase, as we would expect, linked to this increase in STIs, an increase in unprotected, so condomless sex. And obviously this is a significant issue because even though HIV is a really important focus point in sexual health, and even though pre-exposure prophylaxis is inducing some level of protection to HIV in these individuals, we also need to think about all the other infectious diseases that can be spread by this route, syphilis, herpes viruses, chlamydia, gonorrhea, and there's potential that all these infectious diseases could be increasingly transmitted as a consequence of the increase in condomless sex if this is a wider phenomenon. Okay, some other concepts we can explore when we're thinking about prophylaxis. We can think about post-exposure prophylaxis, and again we've talked about it in the context of HIV. It's similar to pre-exposure, but the idea is once someone's been exposed, they can start post-exposure prophylaxis within 72 hours, and it should reduce their likelihood of actually becoming HIV positive, so actually acquiring the infection, because the antiretrovirals are preventing the virus from becoming established within the individual. There are other uses for post-exposure prophylaxis, one of which is to prevent vertical transmission of infectious diseases. So if we have a baby born to a mother who has a particular infectious disease that we can potentially offer a post-exposure prophylactic for, then this can be done in the baby to prevent the disease from establishing. It's not a perfect strategy because it relies upon us actually having these prophylactic treatments. It also relies upon us knowing the status in terms of infectious disease of the mother. So there are challenges here, but it has proven to be a really useful strategy in, again, preventing the mother to child transmission, so this vertical transmission. Okay, and here we have a study that's outlining the use of post-exposure prophylaxis to prevent the mother to child transmission of HBV infection. So first off, the baby, if there's a risk identified, so the mother's been screened for HBV and it's believed she could potentially transmit the infection to the baby, and the baby can be vaccinated immediately after birth, really within 24 hours, but can also be treated with immunoglobulin, so hepatitis B immunoglobulin, so HBIG, and it's been shown that these two strategies together can be really, really effective. So we have an efficacy here of between 85% and 95%, which is great. Again, real challenges here, real challenges in terms of getting everything in place and actually getting this practically done. As we can see, it relies upon screening the mother for HPV infection. Not always possible. People are not always compliant with this, particularly when we consider for many infectious diseases there are high rates amongst individuals who live on the kind of margins of society, so outside of mainstream society. So if we think about drug users, sex workers, individuals who are destitute as well. So these are groups where we see quite high rates of some infectious diseases, including hepatitis B virus. So encouraging these individuals when pregnant to engage in these screening processes can be quite difficult. So there's challenges here, but overall, as we can see, it's efficacious. HIV is another example here. So of course, we want to prevent the spread of HIV from mother to child wherever possible. And one way we can do this is to treat the baby and the mother with prophylactic antiretroviral drugs as soon as the baby is born. Again, challenges here. It relies upon the mother being diagnosed with HIV. Some individuals can be very resistant to getting tested for HIV, and it can put healthcare workers in a really difficult position because there's ethical challenges associated with this. But if there is a diagnostic test of the mother that says she is HIV positive, then these steps can be taken to prevent transmission to the baby. And this paper here suggesting prevention of mother-to-child transmission is extraordinarily effective when using antiretrovirals prophylactically. Another concept that we have discussed but haven't focused on too much is this idea of host variation. So we talk about the immune system and the human immune system, right? But really there are significant variations across individuals because individuals aren't the same. We have individuals with different immune states. Some individuals can be immunosuppressed. We have different genetic features. We have to think about age, and immunosenescence is a concept that exists. So we just have to be aware of the fact that not everyone is equally susceptible to different infectious diseases because there are factors that can impact individual susceptibility. And the clearest one is the idea of a previous infection that we talked about. So some individuals, by virtue of being previously infected by a particular infectious agent, will have a degree of protection. And again, we're not saying 100% protection, and we're not saying permanent protection either necessarily, but a degree of protection is pretty usual to see, really. So that's something we need to be aware of. We also do need to be aware of the idea of immunodeficiency or immunosuppression. This can occur as a consequence of other infections. It can also occur as a consequence of medical interventions, which is something we looked at earlier with HCTs, so transplantations, and of course also genetic factors. So individuals will have inherent differences in their genetic material that can end up in the phenotype as being different levels of compatibility with viruses, and all these factors can potentially matter. And when we're thinking about things like immune state, we're not just thinking about the likelihood of an infection occurring, so whether or not someone will contract a particular infectious disease. We're also thinking about the consequences of infection. So it's often the case that individuals who are immunocompromised or immunosuppressed will experience a more severe infection than individuals who have a fully functional immune system. And this is something we need to understand because, again, there's a significant difference between an infection that has mild symptoms compared to an infection that has quite severe symptoms. And this can come down to the immune state of an individual. And this idea that the same infectious disease can be experienced differently in different people is pretty well established, and it's not always particularly well explained. So there are what we call sporadic diseases. So these are causative agents of disease that can be experienced far more severely in some individuals without a particularly clear understanding on our part of why this might happen. So we have paralytic polio. So less than 1% of individuals who are infected with the polio virus will experience paralytic polio. And it appears to be something to do with CNS involvement, so central nervous system involvement. And as the paper here explains, it's associated with a defect in type 1 interferon production. And as we know, interferon is an immune signaling molecule, so it's involved in inducing the immune system, and then also with CNS involvement. So this is the mechanism of what's going on, but the causes of that are not quite clear and it's not completely understood. But the key takeaway here is there are these differences between individuals, and this is what we want to understand. Okay, and here we're referring to the instance of herpes simplex virus infections causing encephalitis, so inflammation of the brain really. And we can see from this paper that it is linked to polymorphism within TLR3, which is obviously, as we know, TLR3, toll-like receptor 3, which is involved in immune function. Interferon, which we looked at in the last slide, similar. So they're involved in the same immune signaling pathways, aren't they? TLR is a receptor, interferon is for signaling, but similar in the sense that they're involved in this immune signaling. And individuals who have a polymorphism in TLR3 are clearly more likely to develop encephalitis in the context of herpes simplex virus. So it does look like, when we go through the literature, and really encouraging you to look at these papers, that there are different consequences of infection in different individuals that can be tied to differences in immune function that are rooted in genetics. Okay, influenza virus is another example here, but this is an example of differences across ages. So the consequences of influenza virus infection are very different in the elderly compared to the young. And we see this for a lot of respiratory tract infections, particularly lower respiratory tract infections, so infections that impact the lung, because in elderly individuals there's a more likely progression to pneumonia, which is obviously a very serious inflammatory disorder. The immune system ages as an individual ages, and this means an individual often has a reduced ability to combat infection, and it also means it's less likely that vaccination will be able to induce a strong protective response, because again, this concept of immunological aging, so immunosenescence, means that an individual's immune system is not functioning at the same level when they are elderly compared to when they are young. Immunosenescence is the key term, this idea of the immune system aging and losing a degree of functionality as it does so. And if we actually look into the details of immunosenescence, we see there's these massive changes that occur. So everything here is tied to immune function, and you can see really complex multi-layered changes that ultimately result in an increased susceptibility to various infectious diseases. Okay, so there's a lot of information there. What we've really done is explored this idea of the compatibility filter. So we've mentioned some ways that we can close the compatibility filter. Most of those ways won't be particularly new to you, but we did add some new information there and explored them specifically in the context of viruses. And then we looked more at this idea of compatibility. So we looked at some of the other factors that can impact compatibility, and we tried to break down this idea that everyone is immunologically exactly the same, because clearly that's not the case. Clearly there's other things going on. We have to think about behavior, we have to think about genetic variation, and we have to think about age, and these are some of the things that we've explored today.